Good afternoon and welcome to 116, 1117 of the Heidegger series. I will today read a little bit from the book of Jude Curriwan, The Cosmic Hologram. This is one of the best go through for fractality and chaos theory. I realize more and more this is a sort of an easy way into the paradigm of quantum mechanics. It starts, and I went to the page 213. Fractals. Having introduced fractals in general and their self-similar and holographic nature, it's time for us to see just how all-pervasive these underlying patterns really are. While we'll return in more detail later to their universality throughout biological systems and our human choices and behaviors, for the moment we'll focus on how a wide range of scientific disciplines is discovering how they abound through natural phenomena. Before we do though, we need to expand on my description of fractals as being self-similar. For while indeed in many cases they are, to be precisely correct, this self-similarity requires their scaling up and scaling down to be in exact ratios of their basic patterns. Where the dimensions scale up and down at different rates to each other, they're instead more generally defined as being self-affine. Self-affinity is a term that denotes the wider resemblance of the parts of a system to its whole. Self-similarity is thus a specific subset of the more generic self-affinity, which of course still scale invariant and holographic in nature. Studies of planetary topography, for example, demonstrate both self-similar and self-affine fractals, with land surfaces tending to feature self-similar patterning and the cross-sections of vertical elevations revealing self-affine structures. And an example in which self-affine fractals prevail is the behavior over time of stock markets, where the often turbulent contact of the system also requires a further iteration of fractal patterning. The market's volatilities entail more than one self-affine fractal to better track and predict their movement. It was Benoit Mandelbrot's pioneering work on stock price models that led him to coin the term multifractals for the multiple forms needed to describe such complicated variability. In considering the following natural systems, as well as later when we look at biological and man-made phenomena, we need to keep in mind that most of them have levels of variation that can be best understood in these wider contexts of self-affinity and multifractals. Geology and geophysics are full of scale-invariant processes and occurrences that exhibit chaotic behavior whose turbulent nature masks underlying order that is invariably fractal. So fractal modeling throughout Earth sciences has many applications, from the analysis of mineral reserves to the fragmentation of tectonic plates. Throughout, many fractal structures show similarities across manifestations that appear to be very different. such as the topology of elevations revealing self-affine structures. An example in which self-affine fractals prevail is the behavior over time of stock markets, where the often turbulent conduct of the system also require a further iteration of fractal patterning. The market's volatilities entail more than one self-affine fractal to better track and predict their movements. It was Benno and Mandelbrot's pioneering work on stock price models that led him to coin the term multifractals for the multiple forms needed to describe such complicated variability. In considering the following systems, as well as later when we look at biological and man-made phenomena, we need to keep in mind that most of them have levels of variation that can be understood in these wider contexts of self-affinity and multifractals. Geology and geophysics are full of scale-invariant processes and occurrences that exhibit chaotic behavior whose turbulent nature masks underlying order that is invariably fractal. So fractal modeling throughout Earth sciences has many applications, from the analysis of mineral reserves to the fragmentation of tectonic plates. Throughout, many fractal structures show similarities across manifestations that appear to be very different, such as the topology of Grand Canyon and the Idaho batholith, which in 1991 geophysicist Donald Turcotte, then at Cornell University, showed share the same fractal dimension. What about that? We've already noted that coastlines are fractal, but the drainage of river systems and the sizes of mountains within ranges are too. And even forest fires spread out along fractal boundaries. In meteorology, not only clouds but also lightning cascades and the repeating patterns of snowflakes are fractal. And we'll see later how the still greater complexity of entire weather patterns arises from underlying fractal attractors. All chemical processes involve energy, and thus information flows which are inherently fractal. The applications of fractal insights to chemistry and material science are increasingly common, as, for example, where the fractal patterns seen in corrosion phenomena are helping a better understanding of the surface structures of metal. Throughout physics too, the ubiquitous nature of fractal is progressively showing up in all scales. In 2010, Ali Yazdani, then at Princeton University, and his colleagues discovered that these patterns exist at the scale of single atoms in a solid. At the sudden a cocoon, as he then added, no doubts there is a butterfly inside. Another discovery of underlying fractal structure relates to the phenomenon of superconductors that have no electrical resistance and so are so extremely useful in being able to conduct a larger current with no loss of energy. Completely unexpectedly, when researching properties of crystalline superconductors in 2010, Antonio Bianconi and his team at the Sapienza University of Rome in Italy revealed that not only was the crystal structure fractal, but also that the longer the length scales for which the fractal pattern lasted, the higher the temperature for which superconductivity persisted. So engineering such crystals to maximize their fractality could produce materials that are superconductive at even higher temperatures. One of the faults with superconductivity is that so much energy is needed to cool down the things, it becomes quite pricey, and the amount of money you save on electricity is spent on liquid nitrogen and other things. But if you can have superconductivity at a higher temperature, it could be fantastic. At much larger scales, astronomers and cosmologists too are discovering that fractal patterns pervade our universe. Within our solar system, for example, the solar wind, the turbulent stream of charged particles that our sun constantly emits, was found in 2014 by Sandra Chapman and her colleagues at University of Warwick in the UK to have fractal properties. Saturn's rings to reveal a fractal pattern. Further ahead, study of the CMB, the astronomical gift that just keep on giving, has shown that galaxies are also clustered in fractal patterns. In 2012, having undertaken the largest three-dimensional mapping so far of such large-scale clustering, Morag Scrimgeour and her team at University of Western Australia in Perth analysed data from the Wiggle-Z Dark Energy Survey. Using observation by the Anglo-Australian Telescope in New South Wales, the team charted some 220,000 galaxies throughout an enormous volume of space corresponding to a cube with a length of 3 billion light years to a side. At a scale up to 330 million light years across, they did find fractal galactic clustering. Wow! But beyond that, galactic spacing appeared homogeneous, which is in line with the model of the cosmic hologram that we've been exploring. For while fractal scale invariance and other holographic attributes are features of the manifestation of space-time, there is no need for the overall topology of the universe itself to be fractal. Indeed, if it were so, enormous problems for its study would have ensued, not least that our notions of space-time itself and the use of general relativity to model it, which has passed every experimental test it has so far faced, would have been invalidated and would have had to be thrown out or at least radically modified. The largest scale fractal patterning yet discovered by Scrimgeour's team are in agreement with the maximum size to be expected in terms of gravitational organization of matter over the 13.8 billion years of our universe's big breadth. What the repetition of fractal patterning from the smallest to the largest scales shows us, however, is that informational patterns that underlie our universe embody the minimum information and simplest instructions at all scales to enable manifestation of maximum diversity and the development and evolution of the greatest complexity. The discoveries that underlying fractal patterns are universally pervasive also reveal the innate harmonic order of our universe. But for us to continue to see what this means for our wider understanding, we first need to consider what I mean by harmonic order and how its simple rules play out in complicated ways. So next paragraph is harmonic orders. When I was at school many years ago and well before the invention of pocket calculators, in my math class I learned how to use two indispensable tools, log tables and slide rule. And while electronic calculators and computers have long since made both obsolete, how and why they work is as pertinent, and with the understanding of the cosmic hologram and the harmonic nature of reality even more relevant than ever. Let me explain why. What they both enabled was for otherwise complicated sums such as multiplication, division, calculating square roots of numbers to be dramatically simplified. They did this by using logarithms, which convert multiplication into addition and division into subtraction much easier. You'll probably be grateful that I'm not about to go into the technicalities of logarithms. What's key for us here, though, is to appreciate that they operate in the way they do, because essentially they are harmonic. This is owing to their being exponents or powers of a base number, such as 10. Where the base is multiplied by itself however many times to arrive at a required number. To explain this numerically, we need a bit of math. The log of any number x, say 100, is the power to which the base, in this case 10, would need to be raised to equal x. In this case 2, as 100 is 10 times 10. So the log of 100 is the base, 10 is 2, or log 10 equals 2. This allows the conversion of numbers to the log equivalent and vice versa. And the harmonic mathematical properties of logs to be then used to simplify complicated calculations. For optimum means, base 10 or common logs are used in general science and engineering, and base 2 or binary logs in computing science. Base E or natural logarithmic relationships, where E are Euler's number, pervade mathematics and are especially important given the deep connection between E and the complex plane. An essential consequence of their harmonic nature is that logarithms are rather like geometric fractals, in that they are self-similar and scale up and down by factors of their numerical base. Logs are found through many universal relationships, and logarithmic spirals are key features of numerous evolutionary processes. We even see and hear the world logarithmically, because our eyes respond in this way to the brightness of visible light, and our ears to logarithmic decibel scale of the frequencies of audible sound. I don't think most people know that, even though it is pretty basic. It changes the idea of a one-to-one relationship already at the mathematical plane, which is good. Such logarithmic sensory perception enables us to see and hear across a wide range of visual and acoustic stimuli without overwhelming our senses. Natural logarithms pervade Fourier transforms that are basic to the holographic principle. Most significant of all, perhaps, they anchor the fundamental equation for informational entropy, and so again reveal the nature of reality in innately harmonic, fractal and holographic terms. A while back we explored how nothing is ultimately random and considered a common distribution of data, such as the heights of a group of people that overall fit into the so-called Gaussian distribution curve in the shape of a bell, and where the average measure of the group correlates to the peak of the bell. There are, though, many phenomena whose features don't correspond in this way. Some key ones obey instead a distribution based on log-based relationships. These are called power laws and incorporate logarithmic correlations between sizes and frequencies of their occurrences. Crucially, such phenomena are holographically self-similar at all scales over which they apply, and so there is no such thing as an average measure or a typical event. One example was revealed in 1989 by Lindsay McClelland and his colleagues. Studying the relationship between size and frequency of two tranches of global volcanic eruptions, the first going back 200 years and the second the decade between 1975 and 85. They discovered their scale invariant nature over an extensive range. A further such manifestation is the incidence of earthquakes, which follows the Gutenberg-Richter power law for the magnitudes, and where the relationship between the size of a specific quake, as measured logarithmically, has a power law relationship with its frequency. The logarithmic scale uses base 10 logs to measure the energy released. An increase in the scale of 0.2 represents a doubling of the energy, so a massive 9.0 event such as the Japanese earthquake on March 11, 2011, and which was the largest yet recorded there, released 64 times the energy of the still terrifying and disastrous magnitude 7.8 Nepalese earthquake on April 25th, 2015. What this harmonic power law shows is a simple yet crucial relationship that applies to all earthquakes, whatever scale and wherever and whenever they occur. One of twice the size occurs 4 times less often. Such scale invariant relationship between the size and the frequency of power law phenomena reveal two further key insights. First, the energy of each earthquake multiplied by its frequency remains constant. Second, while there are fewer major events than smaller ones, there is no way of predicting the time and location of specific occurrences. The best we might hope for is an early warning system that can measure the stress buildup in vulnerable geological strata, although even then, as a nonlinear process, the size of the stress is not necessarily indicative of the scale of any resultant quake. We may indeed already have such a system, as suggested by British biologist Rupert Sheldrake, perhaps a more open-minded and thorough investigation into the widespread anecdotal evidence that animals and birds may, owing to their inherent sensory sensitivity, show that they do pick up subtle environmental changes, presaging such events like earthquake. Monkeys go berserk already, I think, a couple of hours before an earthquake, so do birds. Sheldrake proposes a hotline or website that people could contact to report strange behavior in their animals, using computer analysis to determine any cluster that aren't attributed to other factors that correlate to subsequent quake can be read into conjunction with other seismological measuring devices. Such an initiative could aid improved prediction and empower appropriate action. The Ferris bond. Another exquisite example of harmonic order is what Plato considered to be the Ferris bond in the physical world. When a line is divided into two, such that the ratio of the smaller to the larger segments is equal to that between the largest segment and the whole. This universal relationship is known as the golden section, or phi. Its numerical properties are astounding, and so significant is its expression throughout nature that it was called by the 15th century Italian mathematician Fra Luca Pacioli the divine proportion. Indeed, Fra Luca wrote a book of the same name, illustrated with beautiful geometrical drawings by no less an artist than his friend Leonardo da Vinci. Its aesthetic beauty has been reflected in the work of numerous artists and architects, and its proportion is even found in the basic shape of modern credit cards. Many profound thinkers too have been fascinated by its attributes and pervasive presence in evolutionary systems, including the World War II British codebreaker and father of computer science, Alan Turing. He writes, mathematically, phi is termed as an irrational number, like pi and Feigenbaum's number, as the digits after the decimal point in its value of 0.61803 continue without repetition forever. Uniquely, 1 divided by phi is equal to 5 plus 1, or 1.61803, also referred to as phi. Earlier in the 13th century, the Italian mathematician Leonardo of Pisa, more commonly known as Fibonacci, revealed other profound aspects of phi for a series of numbers that has come to bear his name. Starting with 0 and then 1, each successive term in the series is the sum of the previous two numbers. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on indefinitely. Phi arises when each number of the series is then divided by the one after. 0 divided by 1, 0 divided by 1, 1 by 1, 1 by 2, 2 by 3, 3 by 5, and so on. By then converting these ratios to decimal form and plotting them on a graph, we find that a wave emerges that pulses progressively closer to the value of phi and recedes even deeper into the fabric of reality, converging on 0.610803. Conversely, phi also emerges when each number in the series is divided by the one before it. 1 through 0, 1 through 1, 2 through 1, and 3 through 2, and so on. Intriguingly, at any rate to me, here the first ratio of 1 through 0 is infinite, while the second and all subsequent terms ground the series in a finite form that this time ultimately converges on the alternative form of phi, 1.61803, although the convergence progresses at a very slightly different rate to its inverse. A beautiful example of the harmonic nature of phi was found in 2015 when astronomer William Ditto and his team at the University of Hawaii analyzed variable stars whose brightness oscillates in a harmonic way. They discovered that sometimes not only were the two primary frequencies of the stellar song in phi ratio, but also that for such golden stars the entirety of their harmonics displayed a fractal pattern. Phi's harmonic nature becomes even clearer when the progressive numbers of the Fibonacci series are expressed to form a special type of logarithmic spiral. These spirals are seen throughout nature, from nautilus shells and whirlpools to the growth of plants and the embryonic development of animals, to the awesome scale of spiral galaxies. Its presence pervades evolutionary and biological systems, and we ourselves embody relationships that approximate to phi in the ways the joints of our fingers and toes relate to our hands and feet, and they in turn to our arms and legs and continue on to our whole body. Even our DNA is in phi ratio, with the width and length of a full cycle of its double spiral molecule measuring 21 and 34 angstroms respectively, both Fibonacci numbers. And angstrom, by the way, is ångström. It's a Swedish name of a Swedish inventor. I think he was in the 18th century, not too sure. The cosmic nature of phi and its harmonic presence isn't merely a feature of Fibonacci series of integers. All series such as the Lucas series, which begins with 2, 1, 3, 4 and so on, whose progressive integers like Fibonacci's are added to the one before, and where each is then divided by its predecessor converging to phi, regardless of the first two numbers. A number of geometers feel this is revealing something profound yet elusive about the deeper structure of reality. In recent years, the mathematics of Fibonacci and Lucas functions has been combined with the so-called hyperbolic geometry that describes flat space-time, named after Minkowski, who not only pioneered its understanding, as we've seen, but was also Einstein's teacher. Such geometry, which enables events and their causality in space-time to be tracked, is the one in which his special theory of relativity is most often formulated. While the real-world significance of Fibonacci and Lucas hyperbolic functions is an open question, I suspect it will be found to have important connections with the beginning and ongoing expansion of our universe. Influences, shape, size, and stickiness. The two key characteristics of manifestly very different phenomena that have probably surprised researchers the most are, first, the very widespread commonality of patterns or relationships underlying their varied appearances, and second, how apparently complicated real-world structures and systems can be effectively computer modeled using simple rules. Both these unexpected results began to be uncovered in the late 1960s. By 1970, an insight of what might be going on was reported by physicist Leo Kadanoff through studying the behavior of critical points at the edges of order and chaos for phase transitions, such as when water vapor either cools down or is put under increased pressure when it condenses to form liquid water. In the late 1980s, more groundbreaking work was carried out by the physicist Per Bach and his colleague Chao Tang and Kurt Wiesenfeld at the Brookhaven National Laboratory on Long Island, New York, who decided to play with piles of sand, increasing the height of the pile by 1 grain of sand at a time. At some point, the addition of a single extra grain caused the pile to collapse. At this critical point, they measured how the collapse could be small, with only a few grains falling down the slope, or result in an avalanche. Rebuilding the pile again and again, they continued to plot other small and large collapses. What Kadanoff and Bach's team and further researchers showed, using other materials and studying both real systems and by running computer simulations, was that the behavior of the ongoing dynamics between order and disorder in such system is in principle exactly the same, completely regardless of their apparent diversity. It's due only to how easy or difficult it is for an informational ordering or disordering influence at one point in the system to bring order or disorder to another nearby. And it's only the basic shape and physical size of the elements of the system that matter, and that affect the type and the scale of this influence, nothing else. In other words, shape, size, and their consequential stickiness are the sole factors that need to be considered to fundamentally understand and model the system. Very important to take note of that. This is not how we normally perceive the world. We perceive it to be much more complex and unreachable for understanding. I think this might be the most major breakthrough in an onward thrust going closer to the Klein bottle, or as I usually call it, true space. What this universality also tells us is that any circumstances that embody the same simple criteria will behave in a similar fashion, regardless of their apparent dissimilarity. Such varied systems belong to a so-called universal class, and when the characteristics of one member of the class are understood, all other members of the same class can be treated in the same way. And because the state of the system only appears to depend on the basic factors of shape, size and stickiness, to effectively model its behavior one can simply exclude all other details, however complicated, that make up its appearance. I think that is devastational on the current idea of super complexity and super diversity, and I would say distance in knowledge. Complexity, the scale, invariance and harmonic order of fractal patterns, power laws and the spread of systemic influences are also aspects of the features of the so-called complex systems, such as those we already looked at, including earthquakes and landscape formation. Here we bring these and other features together to describe the general behavior of such systems and how they can be understood in informational terms. And in the next two chapters we'll explore them more specifically, first in terms of evolutionary biology and ecology, and then in the socio-economic systems that we experience in our everyday lives. To begin with, the complexity generally develops step by step and through non-linear processes, where a tiny event can trigger either a small dislocation or a major upheaval or vice versa, and which take them far beyond equilibrium to a critical state, where they exist at the edge between order and chaos. The spread of such non-linear influences of order and disorder is crucial to their behavior. Not only, however, does such influence take time to effect, in many instances they are also not one-way processes. Instead, they can involve both positive and negative feedback loops that either augment or damp down the initiating influence. The study of complexity emerged from earlier research into chaotic systems, whose outcomes are the result of relatively few nonlinear interactions, and whose conduct is less governed by the past until they pass through a threshold point such as a specific temperature or a level of turbulence, when they tip into chaos. Complex systems, though, embody numerous interactions, and for them history definitely matters. All events in their past accumulate to form their present, and all current events irreversibly contribute to their future. In contrast to chaos, studying complexity is really about trying to understand how simple behavioral patterns can somehow self-organize to lead to an enormous number of often complicated and dynamic relationships that, despite being at the critical edge of chaos, are nonetheless able to exist on a sustainable basis. They can do this as they are informationally underpinned by a fractal attractor, within whose parameters a robust variability of factors can continue to maintain the system, albeit within limits. One such complex system is the weather, whose underlying attractor is named after the meteorologist Edward Lorenz, and whose mapping in the complex plane reveals the beautifully symbolic shape of a butterfly. While Lorenz's first computer model depicted chaotic behavior, in his recognizing the longer-term stability of weather patterns, he decided to look again for complexity. In doing so, he actually simplified his math, ending up with 3 short nonlinear equations from which a complex, dynamic, yet inherently robust system emerges. The specific state of the system at any one time can be anywhere within the limits of the attractor, and the motion of the system never exactly repeats itself. This led him to coin the term butterfly effect in his seminal 1972 paper titled Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Recognizing that very small differences in initial conditions can produce very different outcomes. This also means that despite the enormously more powerful processing power of computers since the 1970s, the weather still can't be forecast for more than a few days ahead. To this needs to be added the generalized classical viewpoint of that we can ignore all factors without the 99th. This is what we're doing in classical physics. We have 99 of 100 or 99.999, and only the rest is quantum mechanical. That means that in generality, when stressed, I would say, there's a very mild stress, we accept it. But look at the butterfly effect, which is something of all physical world. That means that that tiny quantum thing, which is so small that it doesn't matter to ordinary people, is incredibly important. Incredibly important. And this, I would say, is one of the major problems with modern knowledge. We have somewhere generalized, and by that generalization or stress or sloppiness, it's not much of a sloppiness, I admit, it's an incredibly small sloppiness. Building this one or making this furniture, you can be much more sloppy and still not lose anything. But that extremely small sloppiness, that makes all the difference in the physical world. Why is that? Well, after that we accept the classical physical model. It's one of the most determining arguments, because we both live that sloppiness in our everyday lives. We don't feel any reason to do the pain of doing something even more correct. And therefore we automatically lose into classical physics, because all it needs is that tiny, weeny, tiny sloppiness, and then you accepted all of classical physics. So, butterfly effect, I don't think we can understand quantum mechanics without it. You might be asking that if weather can't be forecast, how can climate change be anticipated? And that has to do with what is averaging. Over an average with sloppiness, you can do a prediction because the prediction in itself is rather sloppy. It's coarse. What it says is not exact. Temperature in generality is not as exact, and we cannot trust those values. Too much trust is put on these generalizations that are presently made about the weather, climate change. It builds in a sloppiness in the system. We'll have a look-see at long-term expectations, and we're going to show that those are incompatible with the survival of the poor butterfly. Before we jump into that, we need to ask a key question. How do complex systems evolve to enable the robust levels of sustainability they embody? Early insights were again provided by Bach, Tang and Wiesenfeld in their work on sand piles in the late 80s, and then follow-up investigations on piles of rice by other researchers, honestly. Continuing to add grains to the accumulated piles, collapses both minor and major persisted. A stage, however, came when as more grains were added. On average, the same number of grains topple off the pile, so the amount of sand in the pile remained constant. Before the groundbreaking work, other researchers have worked with systems whose properties require them to experimentally tune, that is, manually alter the coefficients of the system to reach critical points, such as the reduction in temperature or increase in pressure needed for water to transition to liquid water. What astonished Bach and his colleagues was that the sand piles reached this point without any apparent external regulation, and so they described the system as having developed a property of self-organized critically. In their breakthrough paper of '87, they also stressed that the emergence of such criticality wasn't dependent on the exact details of the system and allowed flexibility and variability in reaching its critical state. While providing significant insight into such complex behavior and the characteristics of the process that bring it about, they, and indeed many other researchers who continue striving to understand such systems, are still trying to determine what is that self-organizing about them, how they do it, and what's happening in them that's different from other non-complex systems. To get closer to answering these fundamental questions, we need to understand how energy and entropy, and most importantly information, flew through these structures. Pioneering work by physicist Edward James in the 1960s, physical chemist Ilya Prigogine in the 70s, and many other scientists since have contributed to the following general insights that nonetheless are still being debated as active research continues. Key attributes of such complexity include, first, that such systems are always dynamic and open to slow and steady flows of energy through them, and while far from equilibrium, are able to sustain energetic stability, and so can exist in a semi-steady state. Second, causality prevails throughout such systems, and history matters, as past events are inherent drivers of their future behavior. In other words, such systems are reproducible and can evolve. Third, they embodied long-range interactions that optimize their interconnectivity. Fourth, the selection principle that seems to apply to their developmental states is that, subject to any externally imposed constraints, the flow of informational entropy is maximized. The operation of this principle also tends to most efficiently organize their innate harmonic order. And therefore their level of systemic coherence and resonance. Thereafter, as semi-stable organizations, informational flow gradually decreases to a minimum, ultimately resulting in an unchanging state, stagnation, or death. Finally, such systems optimize the distribution of information expressed as energy, with a distributed intelligence then enabling them to be both robust and capable of repairing extensive damage to themselves. Breakdown or breakthrough. Even when such systems are robust, however, circumstances can arise where their ability to respond and adapt is severely compromised, and they're forced to undergo what are called critical transitions. Even though they are sustainable, nonetheless self-organized complex systems exist in critical states, on the edge between order and the turbulence of chaos. Yet their intrinsic attributes enable them to remain stable within the limits of their fractal attractors, often for considerable periods of time. As more and more evidence mounts, it's becoming ever clearer, though, that many, and indeed perhaps all, such systems have critical thresholds, one or more tipping points beyond which the system inevitably and often suddenly transforms from one state into another. With such a system's innate non-linearity of causes and effects, trying to predict such critical transitions is extremely difficult. The more so because its organization may show little significant change before the tipping point is reached, but after which, like Tom chasing Jerry off a cliff, there is no going back. And of course I'm referring to Tom and Jerry. Not the ice cream, the cartoon. However, given that such complex structures include everything from financial markets and social structures to ecosystems and our global climate, identifying stresses and early warning signals prior to tipping point breakdowns is extremely important to our collective well-being. For this, to take an urgent example, is where the elephant of possibly unstoppable and catastrophic climate change charges into the room, wreaking havoc and potentially crushing the butterfly. Remember how we plan, using the normal sense, as we say, of adding things, something that is constructed through knowledge, with the idea of height being quantity, which didn't exist until a stage in history and still doesn't exist in many cultures. It's an innovation. It's not from the world directly in some weird transcendental way. If we think that we can plan by making things stepwise, ignoring the butterfly effect, our plans will fail. And this is a huge investigation of companies that works. They do not use that model. They use the truer chaotic theory model that takes true planning, not the planning that is just random, which is actually the case in Newtonian classical physics. Although it's not random when you build a house or trying to test the strength on maybe a beaker or something of that sort, but it will be random if you use it on your own life. It will be catastrophic, as Yuri Haval has shown, the Israeli checker of how we plan today, that we are mostly rational and all our plans fail. There's not a way of building a company, for instance, in a Newtonian way. That company will always fail. We need a much stricter order than the classical physics can give us. That sloppiness I mentioned before. In computer models and experiments with the simplest of complex systems, there do, however, appear to be a few features of behavior that characterize the approach of systemic breakdown. The first is a phenomenon known as critical slowing down, or CSD, during which the system recovers progressively slowly from small perturbations, rather like someone with a compromised immune system finding it harder and harder to recover from minor health issues like common cold. As for a person's health, such CSD behavior tends to begin quite far away from what eventually is the tipping point, after which a critical shift in the system is inevitable. Its continuation, though, leads to changes that constitute a second type of process that is called autocorrelation. This relates to the presence of repeating patterns over time of fluctuations within the system's behavior. And when a tipping point is approached, the level of pattern repetition diverges from the norm. Third sign, which arises from instability at the limits of what the existing fractal attractor of the system can handle, is that it becomes more variable, with progressively skewed changeability in its behavior. Systems that are sufficiently destabilized may also exhibit what is known as flickering, where the system wobbles between alternative states before undergoing a sudden transition to one or the other of them. Given their importance, a great deal of research is being focused on identifying and finding ways to measure these early warning signals. But there are enormous difficulties given their levels of subtlety and uncertainty, and the challenges of studying real-world examples. Political dysfunction, though concerning public debate and policy regarding climate change, imperils not only effective global action in responding to the currently perceived longer-term threats, but leaves us helpless in the face of such potential catastrophic breakdowns. I think I round off there. It's long enough as it is now. Thank you very much and have a very pleasant evening.